Hello everyone, welcome to the Click Physics 1 course. Lesson 3, Measurement Errors and Significant Figures. In this lesson, we will learn about measurement error, source of error, accuracy and precision, significant figures, and scientific notation. These ideas are essential because every experiment and calculation in physics begins with measurement. Why do we measure? Well, physics is a science based on observation and measurement. To study nature, we must measure quantities such as length, mass, time, and temperature. However, no measurement is perfectly exact. Every time we measure something, there is always a small amount of uncertainty or error. The goal of a scientist is not to remove error completely, because that is impossible, but to reduce it as much as possible so that the results are as accurate as they can be. Measurement error. Well, measurement error is the difference between the true value and the measured value. For example, imagine a basket that actually contains 43 apples, but someone counts only 41 apples. In this case, the measurement error is 2 apples. And there is a side note that every measurement contains some error. And this example shows that errors can happen even in simple measurements. In physics, our goal is always to make sure that these errors are as small as possible so that our measurements are more reliable. Well, what are the causes of measurement error? Well, measurement errors usually come from 3 main sources. The first is human error. A person may read the instrument incorrectly, record the results incorrectly, perform the experiment incorrectly, or simply not use the measuring instrument properly. We also refer to it as method error because it is caused by the way the measurement is performed. Well, the second source is instrument error. Sometimes the measuring instrument is damaged, poorly calibrated, or not precise enough to give an exact measurement. The third source is environmental error. Factors such as temperature, wind, humidity, or vibrations can affect the measurement and change the result. Understanding these sources help us improve the quality of our measurement. Accuracy versus precision. Well, although they are often confused, accuracy and precision are not the same at all. Accuracy means that a measurement is very close to the true value. Precision means that repeated measurements are very close to one another, even if they are not exactly equal to the true value. A good scientific measurement should be both accurate and precise. We have an example here. Consider a length for something is 50 centimeters. The true value for it is 50 centimeters. The measurements for this object is 50 centimeters, 50.1 centimeters, or 49.9 centimeters. And these are both correct, the true value and the measurements, because it is as close as possible. Let's talk about significant figures. Well, another important idea is called significant figures or significant digits in this lesson. Significant figures are the digits in a measured value that carries meaningful information about its precision. They include all the digits read directly from the measuring instrument, plus one final digit that is estimated. For example, if the length of an object is measured as 16.84 centimeters, the number has 4 significant figures. The last digit is 4 in this number, and 4 is the estimated digit, while the others are read directly from the measuring instrument. In general, the more significant figures a measurement has, the more precise that measurement is. Well, let's look at the basic rules of significant figures. The first one is all non-zero digits are significant. Second is zeros between non-zero digits are also significant. Third, leading zeros are not significant, which means zeros before the first non-zero digits are not significant. They only show the position of the decimal point. For example, 3.0014. Those two zeros are not significant because they are leading zeros and they only show the position of the decimal point. And finally, zeros at the end of a decimal number are significant because they indicate the precision of the measurement. If, for example, with this one we have 3.1400, those leading zeros after the non-zero digits are significant. And these rules help us determine how many significant figures a number contains. Let's apply these rules. First of all, we have the number 328, and as we can see, it has no decimals or anything. It is all whole numbers, and from this we can know it has 3 significant figures. The number 3046 has 4 significant figures because the 0 is between the non-zero digits and it doesn't come before them. The number 0.00432 has 3 significant figures because the leading zeros are not counted. The number 2.0000 has 5 significant figures since all the zeros after the decimal point are significant. Whole numbers ending with zeros, such as 1200, can be unclear. To show the exact number of significant figures, scientists usually write these numbers in scientific notation. What is scientific notation? Scientific notation is, we can call it a convenient way to write very large or very small numbers. Every number is written in the form a times 10 to the power of n, where a is a number between 1 and 10, and n is an integer. For example, 85,000. It can be written as 8.5 times 10 to the power of 4. 206 million becomes 2.06 times 10 to the power of 8. And 0.000043 becomes 4.3 times 10 to the power of -5. And here we are done with our lesson. These concepts are the foundation of scientific measurements and will be used throughout this course. Thank you for watching, and I'll see you on the next lesson.